So let's start the recording, and let me also share my screen so that we can start the course properly. Okay, so first of all, can I check that everybody can hear me well enough, and that and that you can see my screen okay? You can either reply in the chat or you can let me know. Great, thanks, Giova. Great. So, hello, my name is Andy Turner. I work for EPCC at the University of Edinburgh. I'm going to be the instructor on this course. I have a couple of my colleagues from EPCC here to help me out, who will also be answering questions and helping you out if you run into any difficulties. That's Michael and William. Hopefully we'll be able to help you just along as we go along with it in the main room. If you need some more in-depth support, we might take you off into a separate room where we can share screens and talk to you one-to-one to help you out in that way. So normally at the start of this point in the course, I will be saying, so here is where the toilets are, and here is where we're going to go for lunch, and here's where the fire exits are. I'm not going to do any of those things because we're online. Hopefully you all know where the toilets and fire exits are, wherever you are at home or at your place of work. So I'm assuming that you've all made yourselves safe and comfortable in that way. So this course is called Understanding Package Performance, and it's a new course for us here at EPCC that's been recently developed to meet the need of people who are maybe not developing their own software, but do need to understand a bit more about the performance of the software packages they're using on Hpc systems and how that fits into their wider Hpc, wider research workflow. One thing I would say is that because this is a new course, your feedback is really extra valuable to us on this course, both good and bad. So please, we'll send out opportunity feedback surveys at the end of the course. But we're really, really keen for you to fill those in and let us know where we've done well, where we've done badly, so we can improve this course going forward. I'm excited to be teaching it. I think it's a really interesting idea for a course, and I think it's got lots of good stuff in it. But please do let us know if you run into any problems with it, or have any comments on how it could be improved. So there's this course website, which hopefully you would have found from the links that have been sent out in the emails, and also the links off the Archer2 training page for the course. But I will also put the URL in the chat as well, in case you don't have direct access to it. It is useful to have that website open as we go through the course, so that you can see the exercises and have all the information you need to hand, is what I would say. A quick overview of the schedule. As this is a new course, the timings are probably not as accurate as they would be for a course that we've run lots and lots of times. But what we'll do is we'll go along at the pace that you guys are finding the most useful, and make it as useful as possible to you. And we'll agree together when to have the breaks and what to do. Hopefully, we'll match quite well to the proposed schedule. At least that's what I plan. I plan to take the lunch break at the time advertised, because I know people often plan their days around and have other things they have to do around childcare or other things. So we'll definitely plan to take the lunch break and at the time advertised from half 12 to half 1. But the rest of the stuff might be a bit flexible around that. Please do interrupt. Either use the hand up feature of the interface to interrupt me. Ask in the chat, or put your microphone on and ask as well. I'll try and keep an eye on the chat as we go along, but Michael and William will keep an eye on it as well, and will surely will let me know if they see anything that I've missed as we go along. So that's most of the welcome stuff. There were a few other things I just wanted to mention around the welcome. The first and most important part actually is the code of conduct for the training. We've taken our lead from the Carpentries training initiative, and you may or may not have heard of them or been on some of their courses, and they have a code of conduct for their courses, and we've based the Archer2 training code of conduct very strongly on that. And essentially it boils down to being respectful and kind to everybody else on this course, and this applies to both us as the instructors and you as the attendees, and how we all interact together. So using welcoming and inclusive language, being respectful of different people's viewpoints and experiences, gracefully accepting any constructive criticism, focusing on what's best for the course so that everybody gets the most out of it, and showing courtesy and respect towards other course participants. We really want to make this a positive learning experience for everybody involved, no matter what their background is and what level of experience they're coming into the course with. So we ask everybody to try and respect those as much as possible. If you feel that that somebody has broken the code of conduct in their interactions towards you, you can complete a form, and we will look at that and identify it. We're also, you could have also welcome to approach me directly if you want to in a private chat channel and stuff to talk about things like that. And the course structure. So rather than having the more sort of traditional lectures followed by practical sessions, we're following the sort of a much more sort of carpentries inspired method here, which means that we work together along through the course and do the technical work interleaved within the presentation, within the sort of the theory and the understanding. So what we'll tend to do is we'll talk about something, and then we'll do something in the terminal, and I'll maybe do it and then give you guys a chance to follow along and catch up. And I will try to give you a chance to check that everybody's keeping up at regular intervals, and so you can let me know if you're falling behind or struggling. We can adjust the pace as we go along towards that. We also use the template on the website is from the carpentries, but we are not actually an official carpentries lesson here. We haven't gone through all of the verification and review stages for this carpentries lesson. We're making use of their template because it's really, really useful and a really good template for teaching, and they make it freely available and open source for people. We're also going to make use of a shared collaborative documents called the Etherpad. I'll show it to you in a minute and ask you to fill something in. And we use that for people to make notes, put answers to maybe some of the exercises. The helpers and myself can put additional notes in there that help you with the course as we go along. At the end of the course, we take a copy of the Etherpad, we strip out all of the personally identifiable information, and then we make it available as part of the course archive, so any useful information in there isn't lost for in the future. So you can always come back and look. And feedback, I've already talked about the feedback, and we really, really value the feedback. It's incredibly valuable to us to try and improve and make training better as we go along. So I'm going to go back to the main course website page by clicking on this link at the top and talk to you about the and just give a brief introduction to the Etherpad. So there's this section just above the schedule which talks about the collaborative document, or it provides a link to the collaborative document, the Etherpad. So oops, let me open that in a new link. I actually had it open up here, so let me get rid of that. So the Etherpad is essentially just a text document where all of us can type without logging in. It's a collaborative document. So the first thing I'd like to ask everybody to do is, you can see I've added my name, my affiliation on the attendees list. If you could all go ahead and add your name and your affiliation there, so we can take a record of attendance for people on the course. As I said, these details will be removed later on today after the course is finished, before this is archived and added to the course page. So please go ahead and do that so we know who's been on the course. Okay, so while you're doing that, that's got all the sort of welcome stuff out of the way. So what I'll do is I'll start on the first session. We're going to talk before the break. There's not huge amounts of sort of practical typing in the terminal work. We're going to look and think about HPC workflows for a wee while, and then we're going to check that everybody can connect to Archer2, and then we'll have the break. And if anybody's not successfully connected or not got themselves set up, then they can get some help over the break from the helpers and myself, before we come back after the break and start sort of working on Archer2 and look at the HPC package performance in more detail. So Just before I get started on the actual sorts of work, does anybody have any questions or issues with the course and the setup? Nope. Okay, it's all very quiet. And what I'll do also is I will put the Etherpad link in the chat as well, so it's always there directly at the top in case people want it. Okay, so I think then we will just get started and get straight stuck into the workflow section of part of things. This course, I should stress, it is very much an introduction to package performance, not really a sort of an in-depth deep dive into the performance of a particular code, or how to go and profile codes and understand the performance in huge detail. That's the sort of the next step after this course. This is the course is supposed to be the start of somebody's journey, and give them enough information that they can explore understanding performance and profiling and benchmarking, and then either go on to more advanced courses, or hopefully it should give you enough information actually that you can also explore the area on your own as well with, and understand the right questions to ask, and what people are saying when they present material in this area. So in this first section, we're going to have a quick look at research workflows, and in this case, all our research workflows we're going to look at are going to contain an HPC component, because this is the this is what we're interested here really, as primarily as an HPC service. Obviously, research workflows in general are broader than this and can cover many different things, some purely experimental, others around data assembly, and other sorts of things. I think throughout this, it's useful to keep your own workflow in mind, and try to understand and try to keep thinking about how this might apply to your own workflow. Okay. And by workflow here, I mean the sorts of individual components and steps you take from starting a piece of work to generating the actual work data that you can use to do research, to gain insights and new knowledge. So a really simple example, and most of the examples here we're going to use as simplified, so we understand this, that in reality workflows are more complicated than this, but we need to be able to illustrate some concepts here. This is a very simplified workflow to maybe explore the effect of defects in crystal structures. So at the start, you might want to source some sort of crystal structure from either experimental data or previous modeling studies. You might want to then convert that crystal structure into some sort of input format for whatever modeling code you're using. Here we mentioned VASP, which is a popular materials modeling platform. You define the input parameters for what you want to do in the calculations. And that sounds like a short step there, but it actually can be quite complicated in terms of choosing the methods you're going to use, things like convergence criteria, how you choose basis sets, and all those sorts of things, and are play in here. So that step can actually be quite complicated because it's based on a lot of previous research and understanding that knowledge. You upload the input files that you've generated for these calculations to the HPC system. You run some sort of calculation. Here it says geometry relaxation. That might be not what you're doing, but in this case, run some sort of geometry relaxation on the system. Analyze the output to verify that the geometry or the physical, the modeled physical system is reasonable and correct. You can then run some more calculations based on that structure to generate some other things of interest. Download that output from the HPC system to some sort of local resource, be that a local data analysis platform, be that your laptop or workstation for analysis, and then actually do some analysis to generate meaningful results, which then you can actually do to use research. And even though this is a really overly simplified example, there are actually more steps than you might imagine when you actually come to write them down. And actually, even with this very simple example, there's a lot of steps here. Now, and also, as it says here, some of these steps might be repeated, and there may be a loop in there. We'll talk a bit more about that later in this section. And you might want to run across varieties of different input configurations. So, in this case, I'm not actually going to I'm not actually going to ask you to write something in the Etherpad because it's quite hard to write this stuff down. In a normal course where we're all face to face, we'd ask you to talk to your neighbour for a few minutes and to think about your research workflow and trying to break it down into separate steps or components. Okay, and then think about which components are the most time consuming and why. And then also think about why the components have to be in the order that you've described them as well. So this exercise really is about thinking a bit more in a sort of analytical way about your workflow, because often people don't do this, and they just sort of want research is really interesting and exciting generally, right? Or at least the process of starting new research is. I know a lot of actual the mechanics of research can be repetitive and doing the same thing over and over again. But actually, most people just want to get started on an exciting new project. And so they tend to just start doing stuff without thinking in detail about how their workflow is put together. So I'm not going to stop here and provide huge amounts of time for people to do this, but I want you to bear this in mind. I think maybe, so it's just to explain to a rubber duck. I mean, I don't know if you've come across rubber ducking. It's a process we often use in programming where it tries to replicate that experience that when you have a problem, you go and explain it to somebody, you see the solution to the problem, even without them telling you anything. So there's benefit to be gained by talking to a rubber duck about your problem, and you might see the same and explain it to you in the same way as you would a physical person. But I want you to bear this in mind, and maybe it might be a useful thing for you to do after this course or later on, is to think about your workflow and try and break it down into the separate components and think about the ordering of them and why they have to be in that order, and try and analyze your own workflow, your own research workflow in that way. Okay. Well, one of the things you should hopefully realize is that different steps take different amounts of time, and by that I don't just mean HPC time or running a job on a batch job on an HPC system. I mean actual physical time or your effort. Some things might take a lot of time to run, say on the HPC system, but don't take up huge amounts of your time because you sort of launch them and then you can go off and do something else. Okay, so different components take different amounts of time. And one of the things you're trying to think about when you think about your workflow is what is the most time consuming. It may not be a single component, and it could have multiple components with similar lengths, but people are often very keen to optimize their HPC jobs and make them as fast as possible. But if it doesn't actually correspond to one of the most time-consuming elements of your research workflow, then it may be that that's not the best place to start in terms of effort to put into optimize the workflow. That's not to say it isn't useful anyway, and it isn't the right thing to do anyway, but everybody has to prioritize things. Thinking about your workflow in this sort of analytical way should help you decide which bits are worth optimizing and how much effort you can put into optimizing different bits. So, if the HPC calculations don't actually take up that much of your physical time, but downloading the data does, or running an analysis pipeline on the data does, then maybe they're better candidates for at least an initial pass at optimization, or at least prioritizing in your optimization of your workflow rather than the HPC component. So one way to illustrate this is to think about transatlantic flight. Okay, that corresponds to flying over transatlantic. Sorry, I have a sort of slight assumption here and bias, I guess, to people who are in Europe. Hopefully, maybe everybody in the course is in Europe, but I guess it applies the other way in America. You could think of trans-Pacific flight if you're in a different part of the world. Anyway, this has some sort of workflow where you looks a bit like traveling to the origin airport. You go through bag drop and navigate security control, then you board the airplane, you fly, disembark, go through passport control and baggage reclaim, leave the airport and continue your journey. Okay. And so in this step, let's consider, for example, that the flying component is the bit we're going to improve by designing a faster airplane, or paying for a faster airplane. At the moment, the components may take these sorts of time scales, right? So steps 1 to 3, which is getting to the airport and getting to the stage of being on the airplane, takes maybe 3 hours. can take longer sometimes. Step 4, which is the actual transatlantic flight, might be 6 hours. And the final steps of getting off the airplane and continuing a journey may take an hour, can take longer if passport control or border control is very busy, or you're in the middle of a global pandemic where these things are more complicated as well. So, but assuming these sorts of times, which were typical before COVID, flying represents about 60% of the time for this total workflow. Now, if we get hold of an airplane that can reduce the flight time to 3 hours, say something that might be called Concorde, then we can reduce the total time of the workflow to 7 hours, and flying now represents only 43% of the time for the total workflow. Any further reductions in the flying time has less and less impact as the other workflow step starts to dominate. So it comes to the stage where, you know, actually the difference between flying transatlantic, where the flight time is 3 hours and 1 hour, is not that important anymore, because the other steps in the workflow take so long that additional reduced flying time doesn't help you very much in the overall time for the workflow. Okay, so, you know, moving back to the research workflow that involves HPC, one of the things, as I mentioned before, is if the HPC components of the workflow is a low percentage of the total time, or even a reasonable components, but you do some optimization, then the motivation for optimizing it, at least in terms of improving the overall workflow performance, is not actually that high. And that's always something to bear in mind here. You know, we're going to spend the majority of the rest of the course talking about how we can optimize and how we can understand the performance to be able to optimize the performance of the HPC aspect of research workflow. But you should always have this meta question in mind about whether this is the right thing to do, and whether this will have the right impact, the level of impact you expect to have. Okay. Of course, there are other motivations for improving the time taken for improving the HPC component. You know, you might want to maximize the amount of modeling simulation you get for the resources you've been allocated, because most people are allocated finite resources on HPC systems. Or you might want to be able to understand performance better, be able to plan your resources in the future. Or, as we saw in the Etherpad, you might want to just understand the performance of your code better to prepare for future HPC systems or changes in HPC technology going forward. So, you know, I'm aware that there are other reasons for understanding and motivating, understand the performance of HPC other than optimizing the total workflow. But in terms of workflow analysis, it is always worth bearing in mind where it sits within the overall research workflow and what that means for the optimization and the amount of gains you can expect to have in improving your workflow. Okay, so I just want to briefly stop there for a moment to see what questions people have. Does anybody want to ask anything before I move on? Nope. All seems quite quiet. Good. I'll go on to the next section there, but like I say, you know, if something occurs, you please feel free to interrupt and take it from there. So we talked about the overall structure of the workflow a bit, but I haven't explicitly mentioned about the dependencies between the different steps. And this is what we're getting at in the sort of first exercise, which was, you know, understanding why the steps had to come in the order to come in. Because they might have dependency in that simple workflow. There are generally dependencies in the later steps on output from the steps from the components beforehand. So, and it's often true that at least some sections of a research workflow have this serial dependency, where you go from, you need to do something to get some data or output, which allows you to do the next step, which allows you to do the next step, which allows you to do the next step. Okay, but in general, most research workflows aren't that simple, even the HPC bits. And, you know, although there may be dependencies, there's also the options to do the potential to do things in parallel. So, and if we don't have a strict sequential dependencies, or some parts of our workflow need to be repeated lots of times in an independent manner, then we could make the whole workflow more efficient by allowing different components to overlap in time or run in parallel. So, for example, let's go back to our simplified materials modeling workflow. And in this case, we're now looking rather than a single crystal structure. We might want to look at different crystal structures and look at different different temperatures and pressures, different physical conditions that the crystal structures are under when we're running our modeling. So we're going to be sourcing multiple crystal structures now from experimental data or previous modeling studies, and we need to convert these crystal structures into a format for our program. Now we have defining input parameters for plan calculations at a range of different temperatures and pressures. Maybe we're exploring the phase diagram for this material. And so we're going to have lots of different input data sets now, and we need to upload them all to the Hpc system. We need to run all these different calculations, download the output, analyze it from the individual ones, and then combine the analyses and the output to generate the meaningful results for our research. Now there are multiple experimental crystal structures and multiple independent calculations for each of the starting crystal structures. We can have a look at rewriting the workflow in a way that exposes these dependencies and the potential parallelism here. So there's for each crystal structure. This is almost like a loop in a program, right? We're going to source the crystal structures and convert the crystal structures into an input format, and they depend, the step 2 here depends on 1. And for each of the physical condition set, that's each temperature and pressure point, we need to define the input parameters, upload the input data, run the calculations, download the output, analyze the output from the individual calculations. And then finally, once we've got all the data for the different crystal structures, or maybe each of the individual crystal structures on all the different temperature and pressure points, we combine those analyses to generate our meaningful results that we can use to do research. Now, if you assume that we have 5 different crystal structures and 10 different sets of physical conditions, which are actually quite small assumptions, I think, for most people who are doing research in these sorts of areas, we have the potential for running 5 times steps 1 and 2 simultaneously, and the potential for them running 50 times the steps A to E simultaneously. Okay, so rather than doing the whole thing sequentially, we can think about the dependencies, and if we did some planning in advance, we might be able to run things in a much more efficient way. Now, of course, you may not be able to access all of this parallelism because there may be other limitations, like there's only one researcher working on a project and they can do a limited amount of stuff at any one time. But with some thought to planning and potentially some automation, and we'll look at automation later in the course, there is the potential to exploit this potential parallelism. So there's another exercise again to go back and look at your workflow again and identify any opportunities for a parallelism automation that you're not already exploiting. And is there enough to be gained from doing this to make it worthwhile to take some time to do this? Again, because we're not in the same physical room, this is more difficult to do because it really depends on people interacting to complete this exercise. But I just want to keep it as a marker for you to go and think about the HPC part of your workflow again, or your whole workflow, and think about starting to break it down into these components, starting to think about what the dependencies are, and starting to look for opportunities to make it more efficient and to exploit any sorts of parallelism. And as I said before, the temptation of research is just always to get in and start doing work, right? It's exciting and interesting. It's why we're here. What the recurring theme we'll see through this course is taking some time to start to think about the workflow and dependencies between them can give you the opportunity to do things differently or more efficiently as you work through the research. And people often do this actually when they're planning research projects, right? When you apply for funding or when people think about projects, they often write Gantt charts and express the dependencies between different tasks and think about how that works in terms of the whole project. But actually, this is going down into the more finer grained level and looking in the individual task. What are the components and dependencies in there? And how have I thought about them and taken all the opportunities here to try and optimize the workflow, or think about what I could do and how I could spend my time to optimize it beforehand. So there is a direct correlation between the sort of project management and then workflow management here. And most people do some of this sort of work naturally as they work through their research workflow, and it tends to come out, and most people are already doing some level of optimization and have some level understanding of the dependencies. But I also think that it's true that most people haven't taken that time to sort of step out of it and have a real sort of forensic look at their individual workflows and look for the opportunities there and understand the different timescales involved. So I think most people can gain, excuse me, from doing a bit of that thinking. And it doesn't need to be, Irene, I'm not saying. I don't think I'd argue you should be spending months thinking about something before you actually do it. But I do think investing some time at the start can give a lot of benefit in this area. Okay. So for the rest of this course, we're going to sort of focus in a bit more on the performance of the HPC components of the workflow and what we can do to understand them and to give us the data we can then use to think about how we best use our HPC resources, or how we think about applying for using resources in the future and planning that, or even expanding to different architectures and things like that. But I really would like you to try and keep in mind that there is this meta level above that of your whole research workflow, and that optimizing the use of the HPC part really depends on how the rest of the work, the benefit you'll see from that depends on how the rest of the workflow is constructed and how it's put together. And it might not have the impact you want to making your overall workflow. The other aspects come to dominate the total time taken. And we will see exactly this concept again later in the course when we talk about the limits of parallel scaling for HPC applications. Not just the workflow side of things. So this theme will crop up again later on in the course. So that's the end of that section. I'm aware that that section is a lot of me talking and not much actual doing for you as the course attendees. So next section, we're just going to check that everybody can access the Hpc system and give a quick overview of that. And then we'll have a break to make sure everybody can get on and is registered and all those sort of things. And then we'll start actually doing the work on Archer2 itself and looking at the performance of HPC components, and it should be much more interactive. So just before we move on to the look at the Hpc system, I just wondered what questions people had on that or thoughts. And is there anything anybody wants to share or wants to ask for clarification on before we move on? Okay, thank you for letting me know. It's always useful to know that people haven't just gone to sleep, so it's good that you're still actually there and listening. So let's move quickly on. So in this next section, this is just really an overview of the HPC system, Archer2, that we're going to be using on this course, and then a check that everybody can register and get connected to the system. So the Archer2 supercomputer itself is an HPE Cray EX supercomputer with quite a lot of compute nodes. There's two different types of compute nodes. Two different types of nodes you'll come across on the HPC system: login nodes and compute nodes, and all of them have the same processors, which are these AMD EPYC 7742 64-core processors. All of the nodes are dual socket, so there are 128 cores per node. And this image gives an idea of how the full Archer2 system will look. So let me scroll down a bit. So you access either login nodes or data analysis nodes, which aren't there yet in the system because we're still in the sort of early phase of access. And so the whole system is not available yet. And they're connected to the home file system. Then there's a large number of compute nodes, and the access to them is mediated by the Slurm batch system. And connected to compute nodes and to the login nodes is the parallel work file system. In the file system too, there'll be some solid state storage. That again, that's not there in the early access part, so we don't need to worry about that for the moment. The main upshot of this is that only the work file system is visible on the compute nodes. So anything you do where you're submitting jobs and running other compute nodes, all the data has to exist on the work file systems. Otherwise, you'll run into problems and errors. And we'll talk a bit about that in a minute. Okay. The compute nodes themselves on this initial early test version of the system, there's 1,024 compute nodes, giving just over 130,000 compute cores because there's 128 cores per node. On the final system, there's going to be many more nodes, almost 6,000, giving almost 750,000 compute cores. That's coming later on this year. All the compute nodes in the current 4-cabinet system have 256 gig of memory. That's not going to be a problem for us during this course at all because we're running small test examples. And they're all linked together using the high-performance Crate Slingshot interconnect. And access to compute nodes, you can't just log into them. Obviously, it's controlled by the Slurm scheduling system, which supports both batch jobs and interactive jobs. And we'll be making use of the interactive jobs mostly during this course, though we will see the batch jobs later on. As I mentioned, there's 2 different storage systems. There's Home, which is only available on the login nodes and the data analysis nodes when they come. And that's for storage of critical source code and data for the users because it's backed up regularly. It has a disaster recovery facility, so if the site has real problems, the data is still safe. There's about a petabyte of that storage at the moment. When you log in, you'll be placed into your home directory on the home file systems, and the path to that looks something like /home. In our case, the project ID is TA012. So it'll be TA012/TA012, and then your user ID. There's a potential slight source of confusion and distinction between the home file system, which is the storage system on Archer2, and your home directory, which is the Linux concept of a directory you're placed into when you first log in, and is stored in the home environment variable and accessed with CD tilde. On Archer2, the home file system does generally contain your home directories for all users at the moment, but that doesn't necessarily have to be the case always. So you should be aware that there is this slightly different concept here. There's the Linux home location, which is where you put when you first log in, and has these special meanings in terms of environment variables, and the home file system, which is a particular storage technology that's used on Archer2. The work file system, which is the only one available on the compute nodes, but is available on the login nodes as well, is designed for high-performance parallel access, and it's the primary location where people put data where jobs are running. It's not backed up in any way, and there's a lot more of it, obviously, in the home file system, which is backed up. So once the final full systems there'll be over 14 petabytes of fast work parallel file storage on the system. The path to it follows a similar sort of syntax to the home file system, but we'll just work at the front instead of home. And we'll make a lot of use of the work file system during this course when we start running jobs, hopefully in the next section. The classic problem that people run into when they start using Archer2 is that you get an error from your jobs that they can't see any of the data or the executables or the applications you've installed. And it's very often that people put it on home, which isn't accessible on the compute nodes rather than on work. So, the first thing to look at when things go wrong like that looks like a file's not accessible, is that you're running from the work file system rather than the home file system. There's lots and lots of information on the Archer2 system and the Archer2 documentation. It's really quite comprehensive, even at this early stage. There's always being added to. You may be able to solve your problems there, but of course, on the course, please do ask the helpers and myself if you run into problems or you have any questions about the file system. So the first thing I want to check before we get to any sort of break, and I want to make sure that everybody can do, is that they can log in to the Archer file system. So you were sent communications from the course at the beginning of last week and also at the end of last week, encouraging you to sign up for an account on Archer2 to use during the course. I don't think everybody who's here has signed up for an account. I will show you how to do that in a moment. But assuming you have signed up for an account, I'd like you to check that you can log into the system. So let me just put up a question so I get an idea of how many people have been able to log in. First of all, and then Give me a second. Okay, so okay, so hopefully you can see that poll there, and if you could fill in where you're up to so far, that'd be really useful to get for me to get an idea of where different people are so far. Okay, so everybody's answered that apart from myself and Michael. Obviously, we're instructors, so we should be able to sign in. So most people have already been able to log in, so that's just great. For the one person who's not yet signed up, if you go back to the main course page, understanding package performance, the first step in the schedule says download file, set up download files required for this lesson. If you click on that, it talks about SSH clients, but then it has the details on how to sign up for an account on Archer2. If you could do that straight away now, then we can get the account approved straight away and get you try and get you logged in as quickly as possible before the next session starts, because you do need access to Archer2 to be able to do the next session. And it is a little bit complicated because you need both an SSH key and the password. So the one person who hasn't signed up yet can follow that process. We'll make sure that there's always there's helpers here over the break, which is coming up next, to help you out if you get stuck. So please do just ask questions if you run into problems either signing up for an account or logging in. Please let us know, because it is really important that you're able to do that for the start of the next session. It looks like everybody else is okay. So if I go back to the schedule, we're running well ahead of time at the moment. I've gone quite quickly through particularly the Archer2, the overview of Archer2 and connecting via SSH, just because I wanted to make sure that we had enough time for anybody who had connection problems to get them sorted out, or anybody who hadn't signed up got them sorted out. So we're not supposed to come back actually at the moment until 11:30 for the next part of the course. So what I propose we do, given most people logged in already, is we stop now. We're just at about just past 10 to 11, and we come back actually a little bit earlier. So if we have a break for let's say half an hour, and come back at just under half an hour, come back at 20 past 11. That should hopefully help us get the last person, the only person who hasn't sorted out login, up and running, and we can get stuck into the next section, which will take a bit longer because it'll be much more interactive. Okay, so feel free to sign out and sign back in again, but actually maybe the easiest thing to do is just switch off your microphone, speakers and camera on the session, and leave it for the moment. So if you take a half-hour break, we'll be back at 20 past to start again. Okay, I'll get rid of the poll for the moment. And we check the thing that everybody is able to log on to the system successfully. So I think we're all good for the next section. So in this section of the course, we're going to introduce benchmarking and performance, and particularly we're going to look at the questions about why I should benchmark my use of HPC, what the key benchmarking concepts are that that are useful to understand, and think about performance metrics and maybe what the right one is to measure the performance from my HPC use, and then figure out what parameters can affect the performance of my applications. So hopefully at the end of it, you'd understand how benchmarking can improve your use of HPC resources, understand the key benchmarking concepts and why they're useful to you, and be able to identify the correct performance metrics for your HPC use, or at least know how to start going about that. Okay, so there are many different ways you can understand the performance of benchmarking. Understand the performance of HPC applications, and there are different tools you can use. So the primary one we're going to talk about here is benchmarking. Okay, there is a little bit of a section at the end of the course where we talk about another benchmarking's the other side of the coin, which is profiling. But we'll go into that in too much detail. We're going to talk primarily about benchmarking in this course. So before we get started, I just want to make sure we're all on the same page in terms of what we mean by benchmarking. So benchmarking, as I'm talking about in this course, is measuring the performance of something. In this case, an HPC application varies as you change various parameters. And the parameters we can change, the parameters we can measure the performance variation against a few different things, and differ actually from application to application, but they can include things such as the usual the number of parallel processes we're using, and that's usually MPI, though there are other parallel models out there which some codes may use, but in almost all cases on HPC, that's MPI processes. Number of threads we use, and they're almost always OpenMP threads, but again, there are different technologies out there, and some applications might use different things. How those processes and threads are distributed across the compute nodes and tied to the actual cores in Archer2's case, because it's a pure CPU system. But for other systems that have, for example, GPUs or graphic processing units, it'll be how they're tied between GPUs and cores. And yes, sorry, Jovi, the difference between a process and a thread. A process is an execute. I want to use the word. I'm overloading the word process here. A process has its own memory space. Okay, is the fundamental difference. Whereas threads share memory space. Okay, so a process. If you're in one process, you can't look at the memory of another process. Whereas if you're in one thread, you can look at the memory, or the multiple threads can look at the same memory space. So in MPI, we launch multiple processes and we exchange data by passing messages between the processes. So there's an explicit transfer of data from one process to another. In threads, like OpenMP, all the threads can write to the same bit of memory, so they can see updates to memory or to data in memory made by other threads. Okay, that is the fundamental difference. For example, most applications that you run on your laptop or something like that are separate processes. So, for example, say you've got a web browser open, a word processor, they will all be different processes managed by the operating system. And each of those processes may make use of multiple threads to improve performance or to take advantage of parallelism. So, for example, a web browser window, or web browser tab, sorry, may be a single process, but within that tab, you may be running some JavaScript, it may be rendering images on the screen, it may be monitoring some different sockets, and each of those operations within the web browser process for that tab could be a different thread to split up those things and to operate together more efficiently. That might not be exactly how the web browser works, by the way. That is just me trying to make up an analogy on the fly and to help you out. Okay. So the distribution of processes and threads across the compute nodes, and also, for example, using other resources, potentially GPUs, and maybe IO resources and things like that. And also then not just the things about how we launch the application in parallel or distribute it in parallel, but also the calculation input parameters that can affect performance. So different calculations, different applications have different ones. For example, some of the applications I know well from materials science, for example, like VASP, have different parameters that affect how the problem that is partitioned by the VASP program, which can affect the performance. You can have things about time step length. A longer time step may make simulating the total amount of time faster, but may make your calculation inaccurate. The different settings around how often you write out data and to how many processes, all these sorts of things that are application specific, or what data sets you're using, or what model parameters. All these things can affect performance, but are specific to the application that you're using, or the software program that you're using. And one of the complications is we're often not just interested in one of these things. We can often be interested in multiple different things. Now, and the problem that you have with that is the search space becomes very large, and it can sometimes become difficult to disentangle which of the changes you'll make is actually changing performance in what way. And suddenly the search space can become very, very large and very difficult. The other thing I forgot to mention, of course, sorry, that you may want to use benchmarking for is to compare the performance of different software components that are used in building the application. So if you're using a centrally installed application that somebody else installed, this is maybe not so interesting to you, but people who are installing things often want to look at the performance of different compilers. Say, how does the GNU Fortran compiler compare in performance to the Cray compiler when compiling this application, or different libraries? For example, how does the BLAS or LAPACK in Cray's libsci library compared to the performance of BLAS, LAPACK in AMD's own performance libraries, which can affect the performance of applications. So these are different sort of things that people might be looking at. And so that's what is benchmarking. But why would you potentially, most of the people on this course, the way this course is set up is it's designed for people who aren't really building their own applications per se, or tend to use pre-compiled software packages where you think maybe benchmarking might be less interesting for you, because a lot of the optimization work should have been done by the person who installed the package for you. That's part of their job. But but why would you be interested in benchmarking then? Well, for people who aren't compiling their own codes, understanding how your current calculations scale to different node or core counts can help you choose the most appropriate setup for your work to maximize the amount of research or the amount of data that you get for the amount of HPC resource that you've been granted. And that's especially true at the moment when a lot of people are moving, certainly in the UK, a lot of people are moving from the old generation of HPC national system, which is Archer, to the new system, which is Archer2. And it's very different. The architecture is very different, so people want to understand, what's changed and how can I use this new system efficiently. But also, people often want to understand how potential future work scales that allow you to request the amount of resources in applications resources, so you don't run short to be able to do your research, or that you don't just you're not asking for things that are wildly too much, which reduce your chances of actually getting access to resources when people come to review access requests. Benchmark is also commonly used, one we haven't mentioned really so far, is in purchasing new Hpc systems to make sure the new system is the right level of performance for users. However, most of the people on this course, I think, are unlikely to be purchasing their own Hpc system, so we're not really going to delve into that in very much detail. But it's worth being aware that this is a very big topic, this purchasing of HPC systems around benchmarking, and there's a huge amount of resource that goes into that, particularly from the people who sell supercomputing systems such as HPE Cray or Atos Bull or IBM. They have whole teams of people dedicated who just do the job title often includes the word benchmark, because it's their job to benchmark applications, understand the performance that allows people to win those multi-million-pound contracts to provide supercomputers. Anyway, one thing I do want to clarify before we go further on here is that both the software program you're using and the input you're using are important to performance. it is not just the software package that is being benchmarked, it's the combination of the software package and the input data that constitute the benchmark case. And that's because depending on the size of the system you're studying, often it scales in very different ways, even using the same software package. So if I run it using, say, something like GROMACS, if I have a very small system, say a small protein, then that is going to have or a single protein or a small deep strand of DNA, and that is going to scale, that case will scale very differently to if I'm simulating a huge membrane, a huge membrane with, say, an ion channel in it, because it's a much bigger system. And they're both using the same underlying software package, GROMACS, but the performance and the benchmarks you run are going to be very, very different because of the different input sets you're using. And throughout this course, I may have slipped up, I may slip up, and I may, hopefully not so much in the text, but I may slip up while I'm speaking. But I'll try to make sure I refer to this combination of both the software and the input as the application. Okay, and both of these are super important. And this is why when people request resources on Archer2, when they fill in the technical assessment, one of the key things that the team Archer2 to assess whether something is viable for the system is that they have to make sure that, as well as the application scaling well, which most people can find evidence of of software package scaling well, most people can find evidence of that in the literature. That actually the scaling evidence or that people are providing in these technical assessments includes an input case that is relevant to the work that's being proposed, because it is this combination of the software package and the input that is important, not one or the other on its own. It's the whole application. Okay, so to finish off the bit before we get into actually typing stuff into the terminal, I just want to make sure we've got some key benchmarking terminology defined so that you'll know what I'm talking about when I use them. So we're going to use a number of different terms and concepts throughout our discussion. The first one is timing, and this is essentially a measure of the timing for how long it took to run the application you're benchmarking, or for part of the application benchmarking. Sometimes you time different components of the application. This is usually a fundamental measure. It's usually measured in seconds. And so, or it may be time per iteration or time per SCF cycle or something like that, depending on what you're using. But it is measured absolutely in seconds. The corresponding thing to that is something called performance, and that's how measure of how well the application is running, and it's always measured as a rate. Now, the actual unit can differ depending on the application, with common examples being nanoseconds per day, which is used in molecular dynamics simulations of biomolecules often, iterations per second, or for example, simulated years per day, or SCF cycles per second in electronic structure codes. The actual measure used is called the performance metric, but they're always a rate, something per amount of time. Okay, there's the key concept is the baseline performance. So almost all benchmarking relies on some sort of baseline performance to measure performance improvements against. You have to know how much better you're doing, or how much worse you're doing in some cases as well. And this is often the performance on the smallest number of nodes you can feasibly run on for your problem. For the extremely simple application we're going to look at and look through in this course, we're actually going to use a single core, which is the sort of formal definition of parallel baseline, is that you compare the serial performance to the parallel performance. But that is often not possible for most real HPC applications, because there's memory constraints or timing constraints. It just takes too long to run, or it uses too much memory that you can't access on a serial application. So it's generally in HPC, it's the smallest feasible number that you can use for the benchmarking. And then the scaling, which is a measure of how the performance changes as the number of nodes or cores are increased. And the scaling is measured relative to the baseline performance. And the associated concept is perfect scaling, is the performance you would expect to see if there were no parallel overheads in the calculation. Okay, this is hopefully, I know there's lots of terms here, but they will become more concrete as we work through the course. So I just wanted to make sure they were well defined at the start. Finally, parallel efficiency. And that's the ratio of the measured scaling to the perfect scaling. So how well you're doing compared to how well you possibly could have done, given no parallel overheads. Oh, sorry, there's a typo there. Your application use and benchmarking, that should be there. So there's a short exercise here to think about your use of HPC and to think about the applications you're using, and trying to identify the timings and the performance metrics you might use when you're benchmarking and why you think the metrics you've chosen the correct ones for your case. It may be very obvious, for example, I've already mentioned GROMACS. GROMACS always prints out at the end of each run the performance metric the calculation time and the performance metric in nanoseconds per day, in seconds and nanoseconds per day. So in those cases, it's pretty obvious. In some other, particularly applications that have been developed in a more research setting or are less widely used, it might be less clear, and it may take more thought to work out what you're going to use. So we're not actually going to use one of these sorts of production applications for the work we're going to do in this course. We're going to use a toy example to allow it to run in short of time and to make sure the data volumes are such that we can analyze them easily and illustrate things here. But as we're working through this, it's worth bearing in mind what would you do for your application that you're going to use, and what is there a defined thing you can that's defined that you can use already, or are you going to have to think harder and come up with your own measurements? Excuse me. Okay, I just want to stop there for a moment and check and give you the opportunity to ask questions before we move on to the next session, or the next section, sorry. Anybody got anything they want to ask? Anybody struggling to think of how they might do this, how they might think of a performance metric for their application? Going to sound like an echo, I think, and I'm going to sound like a broken record for the whole of this course. Plan what you're going to do before you do it. Don't just jump in and start doing stuff, even though it's always tempting to do that. What are you planning to measure, and why are you planning to measure it? As I said at the start, you'll often be wanting to vary multiple things when you're doing your benchmarking. Say core thread placements, number of cores or threads used, different input parameters to the program. If you vary everything at once, it becomes very difficult to interpret the data. So you tend to only want to vary one at a time. It's a bit like exploring phase space, if you know that concept, right? You want to vary one parameter at a time and map at the space out so you can understand how the performance varies on different axes. Benchmark performance generally should be measured multiple times to assess variability. So just doing one benchmark run a certain number of cores is usually not considered sufficient. 3 individual runs are usually considered the minimum, but more are better. This can be challenging if you're running very, very large benchmarks, where it's very expensive to run, or it takes a long time to schedule them. And if you can only get one run in on a certain size, you can only get one run in on a certain size. You do the best you can. But generally, you should, as much as you can, do multiple runs so that you can see what sorts of variability there are in the performance results. And you haven't been hit just by a really bad time or a really good time. And we're going to discuss later on in the course how you combine these multiple runs properly to produce a single value that you can use for your benchmarking. Try and capture all the relevant information on the run, as most HPC software captures a subset of this. So things like core counts, how many cores are used, how many nodes are used, how many threads, how many input processes, how they're distributed, when you ran it, all these sort of things, so that you can have this sort of metadata to help you understand the performance of the data. The problem is that if you don't think about what you want to record beforehand, you can go away and measure some data, and then by the time you get to the end, you want to analyze it, you found the bits missing, so you just have to repeat everything again. So it's really thinking very carefully on what data you need at the start is really important, because otherwise you just have to do things over and over again. And honestly, I've been hit by that myself so many times, and just diving in and doing stuff without taking even just half an hour to write down what I wanted to record. It would have made a huge difference, and stopped me having to repeat lots and lots of work. So that practical point's more about my failures rather than, I guess, sort of anything else. And organize your output data so you know which output corresponds to which runs in your benchmark set. I think that's reasonably obvious, but it's surprising how often people get hit by that, and you ask them for, where's the output corresponding to this run? I'd like to see that, and they're just not able to produce it because they don't have the data organized properly. Okay, so we are going to benchmark a simple image sharpening program that, if you've been on any EPCC courses before, you may well have met before. It's one of our favorite programs we use for looking at parallel performance and understanding how parallelism works on HPC systems. We will run this benchmark to extract some timings and convert that into performance data. And then we'll look, once we've collected everything, which is the subject of this section, we'll then look at how to interpret and analyze the data. Okay, so the parameter we're going to vary is the number of MPI processes for this application. We're not doing anything more complicated than that. We're not going to change any input parameters or anything like that. We're just going to vary the number of processes it's used, and then look at how the performance varies with respect to this. Obviously, in the real case, things might be a bit more complicated than that. But so let's start, get started out. So hopefully you can all follow in. So if you're not already logged into Archer2, log in. So I'm going to do that because I forgot to do that over the lunch break to get myself logged in. Oops. This is where you get to see that I can't actually type my password correctly. Oh no, there we go. I can. Can everybody read my, if you can't read my terminal, if it's too small, the text on my terminal, please let me know if it's too difficult for you to read, and I can make it a little bit bigger. I've increased the size a bit, but I'm not sure it's quite enough. So if you're struggling to read the text, let me know, please, and I will make it bigger. Okay, so we're logged into Archer2. The software that we're going to use has been made available as a central module. So we're going to do that first. So we're going to module load training sharpen. There we go. And now we're going to move to our work directory. If you remember from the session before, just before the break, we need to be in the work directory to be able to run jobs, because that's the only file system that's visible on the compute nodes, and that's not where we are now. So where we are now is our home directory. So yours should look similar to this, but with a different username at the end, and we're going to move to the equivalent work directory. So I'm going to go to cd work, and then I'm going to steal the rest of this path, because it's exactly equivalent on there, and it should be hopefully, well, it may be an empty directory. If you've already been doing stuff, it will be actually empty, but I haven't done anything here, so my directory is totally empty. Okay, so hopefully we've managed to load our module. We got to the work directory. I'm going to make a directory to keep my results in, and so all my benchmark runs, called sharpen bench, and then I'm going to move to that directory. Again, empty. The first thing I need to do is get my input data. So let's do that. So it's copy $sharpen input / fuzzy pgm. I don't know why it's put that funny backslash in front of the dollar. The tab's not working properly for some reason. And I'm going to move it to this directory. And there we have some sorts of data. If you wanted to download this PGM, it is actually an image that you can look at. It's a fuzzy image, and the Sharpen program takes fuzzy photographs and, as it says, sharpens them up. Actually, we're not going to look at the input. In this case, it's not important what it actually does, because we know it does some parallel computational work, and it reads in some data and it writes out some data. That's all we're interested in for this case. You can have a look at the image if you want. If you download it and you've got the right source of programs, look at PGM images. Okay, so I've got the image there. It's not a very big image at all, but that's fine. So first of all, we're going to take a look at the baseline performance. Okay, and remember, as I said, that for real parallel applications, you're not going to be able to you're not going to use a single core usually for your baseline. For this very simple application, we can run on a single core on a single compute node as our baseline performance. In general, you should just try to use the smallest size you feasibly can for your baseline, and that may be limited by, say, memory or runtime or something like that. So I have a horrifically complicated srun command here that should allow us to run on a computer. Let me break this down a little bit for you, so just to make sure you understand what we're doing here. So the partition and QoS, quality of service, are needed for every job on Arch. They specify which essentially queue the jobs go into. Okay, there's some slightly different queues on Archer2, but here we're using the standard ones. This reservation flag is a special reservation that's been created for this course that gives us exclusive access to a set of compute nodes. What this means, the reason we do this is that so that you don't have to wait in the queue. To run the examples here when you're on the course. In general, you won't have a reservation when you're running on an Hpc system. You just submit to the general queue and you run when there's space for your job. The account is our project code. That's where the budget's charged to for this course. These two options, minus hint no multi-thread and minus distribution equals block, are required to get the right process and thread placement on compute cores, on compute nodes on Archer2. So they go in every srun command. This is our resource request. Request it minus nodes equals 1. We want one node, and we want one task per node. So that's one core on a single compute node. We give it a maximum runtime of 10 minutes, which is plenty for this example. Then we give it the name of the program we want to run, or the software we want to run, which is sharpen mpi.x, which is an executable. It knows that the input file is called fuzzy.pgm, so we don't need to tell it that. And then we're going to redirect the output from this program into a file called sharpen one core 001.out. You'll see why. So this is gives me some data on the runs built into the file name. So one core we're running on one core. 001 means it's run number 1. Okay, because we're going to do multiple runs of this baseline. So I'm going to copy and paste that because I don't really want to type it all of it, and I'll show you in a minute how to make it easier so we don't need to do this horrible long command line every time. But let's try that. And this is where it fails because I'm doing a live demonstration. Okay, so it went away, it ran the calculation hopefully, and you can see that it's done. Oh, so let me do an ls minus l, I'll make sure better. It's done a couple of things. One, it's produced some output, which is sharpened.pgm. That's the sharpened version of the image from the fuzzy input we gave it. And it's also created this file that I told it to create. Okay. Before we go and look at that file, I'm going to show you how to shorten that command, so you can make it easier to type each time. What we're going to do is going to create what's called an alias, which is a new command based on an existing command, and we're going to give it all of the options that aren't going to change on each of the benchmark runs we're going to perform, and that's the specification of the partition, the QoS, the reservation, the account, and these options for distribution of processes that have to go along with every single incantation that we make. So I'm going to define a command called srun opt. That's srun with options. That is srun with all of those defined options. Let's do that. Okay, so I've done that for this session. You can make aliases permanent by adding it to the end of your bashrc file in your home .bashrc file in home directory on whatever system you're using, in this case Archer2. I'm going to do that in case I get logged out again, so I don't have to reset the alias. So I'm going to copy this command, then I'm going to open the file. So tilde is my home directory, .bashrc. Oops. RC is the bash configuration file. It's empty at the moment, so I'm just going to insert that alias and then save that file. You can do that step if you want. You don't have to. If you don't do it, every time you log in, you need to redefine the alias before you start using it. Okay. So now we can run the baseline calculation again, and it should be much easier to specify, because this time we can just type srun opt. We can give it the number of nodes and the number of cores per node, or processes or tasks per node equals 1, and we're making it sharpen MPI.x, and we need the time, of course. Sorry, I forgot the time at the start, otherwise it will complain that I haven't set a time. And this time I'm going to output it to a similar file. Instead of 001.out, I'm going to call it 002.out, because this time it's the second one of our baseline. Let me do that. Oh, and it's n tasks per node, right? Because I can't type, apparently. Let's do that. Okay, and it should have created the file again. So there's a 2, and we'll do one more of them. And the only thing I'm going to change on this time is I'm going to change it to 03. That's going to be the third run of the baseline. Okay, and so now I have 3 output files. So can you have a, if you haven't already, have a go at running those 3 baselines, define the alias if you want, and so you've got 3 output files and the similar to the ones I have. And then we'll have a look together at what they mean. I'm going to create a short poll here just to make sure, see where people are up to with this so far, to make sure we've got everybody keeping up. So Helen's asking, how does 002 differ from 003, and does it? We'll have a look in a minute, but yes, potentially it will, because each of your runs may take slightly different times, slightly different amounts of time to run, because of sort of natural performance variations. So one node may be running a little bit cooler or a little bit hotter than another one. They might be running other processes in the background to run the operating system and things like that. So there will be some sort of natural variation in the timings and the performance. You would hope that they would be very small, especially for a small application like this. For a larger application, it may be that the differences are larger. Okay. So I think just about everybody's there. So let me finish my tea. I'll switch off the microphone so you don't hear me slurping tea. Go and chat to them and check that they're okay and where they're up to, please. One of you. Oh, Alessandro got an error. Okay, thanks, William. If you could help Alessandro with his error. So Alessandro, do you have are you using an Archer2 account within the training course, or do you have one via another route? Okay, okay. It depends which account you're using. I'll get William to help you out. I think that one should be pretty easy to sort out, hopefully. I'll carry on for the moment, but William should be able to help you get that up and running. Okay, so we've done our 3 runs. Let's have a look at the output of one of the runs. So I'm going to I'm going to use cat, which just prints the content of the files to the page to the page. Sorry, I did mean to say at the start of this. Sorry, just let me stop. Go back. If somebody is using an Archer2 account that's not part of this training project, so it's an Archer2 account that you didn't apply for through the TA 012 project, then you need a different incantation on the command line, because you won't have access to the reservation, and you may see an error like Alessandro saw there. I put in the Etherpad, the alternative syntax you should use. So most of the options are the same. The only things that change are the QoS, which becomes short, and the reservation, which becomes short QoS. That should push you into the short queue on Archer2, which means you get fast turnaround time, even though you don't have access to the course reservation. Sorry, right, now let's get back to the course. Okay, so here's the output from the Sharpen example. There's a certain amount, it has some useful data in it. It has the image size, which tells us the amount of input data we're working on. It tells us that it's starting the actual calculation. That it reads the image file, it starts the calculation, writes the output file, and then it gives us two timing numbers. It gives us an overall runtime and a calculation time. The overall runtime is how long it took for the whole program, the whole application to run, which is just over 3 seconds. The calculation time is just this bit in the middle here. So that's the time, but without the time it took to read in the data or write out the data, just the time it took for the parallel sharpening calculation to run. So it gives us two different timings. Okay, and based on this information, we can propose two different timing and corresponding performance metrics. There's the calculation time and the overall runtime, which we've talked about and I've described already. And then we could define a calculation performance in, say, megapixels per second, which is the calculation time divided by the size of the image in megapixels. And the overall time, the overall performance in megapixels per second is the same, but with the overall time divided by the image size in megapixels. So for my output in the actual course material, the image size was 564 by 770, which is the same for you. So that's, to get the megapixels, it's that times that divided by 1,000,000. So that's just 0.43 something megapixels. Had a calculation time of just another 3 seconds, overall time of just over 3 seconds. So we can get the calculation performance as number of megapixels divided by the time, so that's 0.151 megapixels per second, and the overall performance in the same way, leading to a slightly lower performance because it took longer. Okay, so the lower the time, the higher the performance, right? Which is exactly what you'd expect. So now we have 3 sets of data for our baseline rather than just a single result. We need to combine them in some way to produce our final performance metric. Okay, you see it's the performance metric we're aiming for here, not the final timing, really. The performance metric we're interested in. And how you combine things depends on what you're measuring and why. Okay, so it's slightly more complicated, and I'll say which one we're going to do. But you may want the idea of the worst case scenario. This allows you to be conservative around requesting resources for future applications to make sure you don't run out. In this case, you usually want to use the worst performance at each of your parameter values. And that's core counts for our sharpening examples. And so that would be the longest time, which would give the worst performance. If you want an idea of the amount of work you're going to get through the current resources you have, you might want to take some sort of mean of the timings. And the best way to do that is to take the arithmetic mean of the times you have and then convert that mean timing into performance metric. You can't really combine rate metric results using an arithmetic mean, as it leads to incorrect conclusions. So you're almost always generally better combining the results of timings and then converting this result into a rate. If you need to combine rate metrics because you don't have access to the timings for some reason, then you Hello, sorry, I think I disconnected at some point there. I'm not quite sure when I stopped. When you stopped being able to hear me. Can you hear me now? Okay, fine. Sorry, so I'll go back. Okay, fine. Thank you, Helen. So, yeah, so you don't generally combine rate metrics, performance metrics using the arithmetic mean because it can lead to incorrect conclusions. It's much better to combine the timings first using the arithmetic mean, and then combine your mean timing into the rate. If you do need to combine the rate metrics because you don't have access to the timings for whatever reason, then you can use a harmonic mean to combine them rather than the arithmetic mean. If you want more information on combining data from benchmarking and best practice, there's this link here to a paper by Thomas Hoffler called Scientific Benchmarking of Parallel Computing Systems, which gives a lot of detail and information on how you combine those things. Well, a good rule of thumb is combine your timing data before converting it into a rate if you're going to use means. If you want an idea of the best case scenario, to allow you to compare the performance of different HPC systems or particular choices, you might want to take the best performance for each of your relevant values. In that case, it's the lowest timing for us. And in our case, this is core counts in the sharpening example. And sometimes you might want an idea of what the performance variation is. This is often what we use as a service provider for Archer2, is we'll monitor the performance of particular applications, and we're interested in how much it varies. What's the difference between the best and the worst? Because that tells us, how stable the system is for different workloads, and then if there's big variations, we can go and look at what the problem might be and why they're being affected in that way. So often then you'll want the best difference between the best and worst, or maybe as a percentage of the variation of percentage of the mean performance. In any case, for this example, we're interested in the change of performance as we change the number of MPI processes or the cores we use. So we're going to use the minimum timing value, which corresponds to the best performance we measured from our multiple runs, the maximum performance. And we can look at this, we can try and have a look at this using grep. So if we grep all of the data files we have at the moment and just search for timing. So grep, if you're not familiar with it, is a tool that searches for a string in a text file and only prints the lines where it finds that string. But we could only print the timing data by grepping for time in our .out files. So let me do that. So grep, oops. So I'm going to grep for the string time in all files that end in .out. That's start. Okay. So we can see if we look at the overall runtimes in the three cases, the first one ran in 3.134, next one ran in 3.213, and the last one ran in 3.293 seconds. So actually the best performing one was my first one, because it has the lowest timing value. And that's actually true of the, almost true of the calculation as well, but it's not quite true of the calculation one, because the best performing one for the calculation was 1.3, where the time is slightly less than the one in time one. So it is slightly more complicated than that. But you could assess which one the maximum and minimum is that. Now, of course, then you have to actually take this data and combine it. And that could start to get a bit tedious if you've got lots of output files. So we've made it a bit easier for you here, and you can do the same for when you're extracting your own things, is we've written a small Python program called sharpendata.py that takes the extension of the output files, which is out in our case, and extracts the data required to compute performance in the image size and the timings, and saves them, prints them to the screen, but also saves them as a CSV file for you to be able to manipulate in the future. So let's try running that. Should already be in your graph. So sharpen data I, and the extension we're looking for is out. Okay. So this small program has taken our three data files, read them, tells us how it produces 3 columns of data. One, the number of cores it ran on, the image size in megapixels, the calculation time, and the overall time. Okay. And then it also, sorry, I've used it up here, should have produced a benchmark runs.csv file, which contains that data as well, which you can use in future in the commonly separated value format. Okay, so go ahead and use that and make sure your runs have been combined too. So hopefully that's given us our baseline data. We've done 3 runs, great. Now we need to collect the benchmarking data more generally as we increase the number of cores for this application. So what I'd like you to do in this exercise is run a set of calculations in a similar way to what we've done already to benchmark the performance of the Sharpen MPI program, the application with the same input file, up to 2 full nodes, 256 cores. You want to make sure you keep the program output in a suitable set of output files that you can use with the Sharpen data.py program. So that means they all need to have the same extension as that one. That's what it depends on to read the data. If you want to, you can write a job submission script to run these benchmark calculations rather than SRun directly. I know some people are already Archer2 users here, so they might be comfortable doing that. You don't need to benchmark on every core count between 1 and 256 is my first thing. I would think, I would say just double each time, and that's probably the best way to go. So you've got the data for 1, you should also maybe do 2, 4, 8, 16, 32, 64, 1 to 8, and 2, 5, 6, and you'll need 3 runs of each of them. I'm going to put up a poll to allow people to mark whether they've completed this exercise. But if you need help or you're stuck or you have any questions, please just ask and we're more than happy to help you. Okay, fine. So have a go at that. Where are we now? We're at 12:09. So maybe give you probably 10 minutes or something to have a go at that. That'll take us to about 20 past 12. And that'll give us 10 more minutes before lunch to look at something before we finish up for the break. Okay, so yeah, so writing a job submission script has some subtleties in terms of the shared libraries. You need to add a line that is module load EPCC jobenv, EPCC-jobenv before any other modules are loaded in the job script to make that work. Okay, it is a bit more complicated. We'll look at job scripts. We're going to look at job scripts when we come to automation, and later on, so you'll see that. If you want, great. If you haven't quite managed to get all the data, don't worry about it too much yet. You can either just keep working on it to get it, and then follow up the examples as and when, follow the rest of it as and when, and you get the data. Your other option is I put the data I generated in a shared folder, so you can always copy that across and use that for doing the analysis if you're struggling to get your own set of data in time. So let me see where we're up to. So I will put in the Etherpad how to get the example data. So from your own account, you do a CP. Probably want to get the whole folder, so we'll do a -R to get the whole folder. And it's work K012 shared example data and copy it to local location. And you can use that to get an example data set if you don't quite have one now, or you can just keep working to get your data set as we run through the next stages. I'm going to stop the poll for now. And we'll move on a little bit. We're not going to go much further, and then we've got lunch. So what I'll do at the end of the lunch break, as I'll stick around at the start of the lunch break for 5 or 10 minutes to check if anybody's got any questions as we run into problems generating data. And then before we start the next session after lunch, I'll check that everybody has some set of data they can work with, either the example data set or one they've generated themselves. So there is a solution here, which is hopefully you just ran. You can see what I did here, actually. It wasn't very sophisticated. I just repeated the command 3 times for each core count. The only slight subtlety was when I got to 256 core example, I had to put nodes equals 2, but then task per node stays the same. It's 2 times 120. There's only 128 cores per node, so I went 2 times 128 to get 256. Okay, and now we've got all these output data. I should have lots of output files here. See, we've got out for each of the different sizes and for 3 runs in each case. And I could use the sharpen data .py short little script again with out as the extension. That should get me the data from all of my, should process the data from all of my benchmark runs. So you can see here's the different core counts, and there should be 3 copies for each different core count. The size of the image stays constant for all of the different runs. The calculation time changes, and the overall time changes. And it should also have produced a CSV file called benchmarkruns.csv, which contains the same data but in a CSV format, which we're going to look at using in a little bit. Okay, so the next thing we want to do is take the data from our multiple runs and aggregate it. And we spoke earlier about aggregating data and the best practices for aggregating data, and we said at the start of this section that we were going to aggregate our data to get the maximum performance. Okay, so now we're going to do our aggregation using a tool that's installed on Archer called VisiData. VisiData is a tool written in, an open source tool written in Python that gives you sort of spreadsheet-like interface within your terminal window. It can be really useful for actually doing quick manipulations of data with CSV files, and actually, as we'll see in the next section, getting quick visualizations of data in photographs in the terminal without the need to worry about having X windows installed or downloading files to plot them locally. You could just as easily, or you could as easily, if you're happy or want to do that, you could copy the CSV file we just created back to your local system, and then use something like Excel to complete exactly the same sorts of tasks as we're going to do using VisiData. So if you're more comfortable or you want to do that, then please feel free to do that. If you want to do VisiData along with us, along with me, then that's fine too. Either of those things should work. Or either of those options should work fine. You could also, of course, write little scripts to do all of this as well. But for ease of use, we're not going to do that. We're going to use the existing tools. So let's get the data into VisiData. So we need to do 2 things. We need to change the default Python to the Cray Python distribution that comes along with the system, and then we need to load the VisiData module, and then we can use the VD command, which launches VisiData with our CSV file to load it. So I'm going to module load Cray-Python, which gives us access to this to the Python 3 that's distributed along with the system. Module load VisiData to load the VisiData tool, and then VD starts VisiData, and we give it the name of our CSV file we want to operate on. Okay, so the 2 module loads, and then VD, and refresh return. And this gives me a spreadsheet-like interface. So I can move around, I can move down rows and up rows using the arrow keys, and I can move across columns using the other arrow keys. You can also use the mouse. It depends on how different terminals are set up, but you can use the mouse as well to move around. So one of the powerful things that VisiData allows us to do is to aggregate the data based on the input in a particular column. Okay, so we're going to aggregate the data across the number of cores. So every time we see 16 cores, we're going to fix the maximum value for the timings for the calculation and the overall. To be able to do this, VisiData needs to know what type of data it has in the columns. It doesn't infer that automatically, so you have to tell it whether it's number data, either integer number data or floating point number data. So integers are whole numbers, floating points are things with a decimal point in them. So I'm going to do that, and the way you do that is with keystrokes. So to set the cores column, which is integer data to integer data, I press hash or pound, depending on whether you're American or British European or European. To set, so I've done that for the cores column just by highlighting a cell in the cores column, pressing the hash key. For the size column, that's going to be floating point data, so I want to use the percent key to mark that up, and the same for the other ones. They're all floating point data. So I should use percent key for the floating point data and hash for the integer data, and that converts the columns to the right sort of input format. Okay, and you can see your output should change to look like that with the data now right justified to show it's been identified, and the column names will have the type in them, either hash or percent. Now we want to do the aggregation. Okay, so we highlight the calc column because column we want to aggregate, and we should use plus, and that gives us a little menu at the bottom where we can select how we want to aggregate them. And in this case, we want to aggregate with the minimum timing value because that corresponds to maximum performance. So I'm going to select minimum by pressing. So I can move up and down here again, but minimum is already selected. I'm just going to press enter. Okay, so we selected minimum. If you notice at the bottom when I highlight this column, it now says there's an aggregation set of minimum. I'm going to do the same for the overall column, so that's plus, and then enter to select minimum. And I'm actually going to do the same for the size column as well, because I want to make sure the size column comes through when we do the aggregation. In this case, it doesn't matter whether we select minimum, maximum, average, because they all have the same value. So for sake of convenience, I'm just going to choose minimum again. So all of these columns now have the minimum set. Now, finally, we're going to aggregate to the cores column. We use capital F, essentially Shift plus F to do the aggregation. Okay, so that said, on this column, select unique values, aggregate from the other columns, and you'll see what I end up with is a column that has the count. That's the number of values it found with that core count. The size, the minimum of the size, but that doesn't matter because it's all the same. And then the minimum calculation value and the overall minimum, the overall timing minimum as well. Okay. So we've created an aggregate. We've now aggregated our data across our multiple runs using VisiData. Okay, so it should look like this. The final detail we've got here before we're going to save this data is the cores. We want to order this cores column, but we want to order the data by increasing core counts. So to do that, I use the left square bracket to sort ascending on that data. So I highlight the cores column, just the blue one here, and hit the left square bracket, and it organizes all the columns with increasing core count. Okay. Finally, I'm going to save this data, and we use Control S to save, and it'll ask us for a file name. So let's do Control S. You should see at the bottom here, it asks you to save to this. It's suggesting this file name, but that's not what I want to save it as. I want to save it as something called benchmark_ag.csv, which is the aggregated value. I want to make sure it's a CSV, not a TSV, because I want it comma separated, not tab separated. The benchmark ag.csv, and then press enter to save it. Okay. So, and then it's saved it for us. Now I can exit VisiData by typing G then Q. Okay, that gets me back to my command prompt, and we hopefully should see we've got a benchmark ag.csv file, we can look at. Okay, so that's us with all of our data aggregated, saved to an USC file. So to exit Visi data, it's here, it's just type G, then Q, not them together, just G and then to exit back to the command line. Okay, so what I'm going to do is, it's just past 12:30, and that was when the lunch break was going to be. So I am going to stop now because I know people have to plan their days around the schedule given in the course, even though we're not quite at the end of this section, but we almost are. That hopefully should give people a chance, maybe if they've got time over the lunch break, to finish the benchmark runs. You don't have to if you don't want to. You can just continue. You can use the example data that's specified in the Etherpad to copy over. At the start of the next session, I'll check we're all up to speed and got this benchmark ag CSV file, and then we'll carry on with the rest of the material this afternoon. We'll start again at 1:30. Just before we finish, has anybody got any questions on what we've done so far that they want answered? I will stick around for just about 5 minutes or so in case people have questions or have something they're struggling with. And I will try to be back a little bit before 1:30 as well to answer any questions before we get started again. As before with the break, it may be the easiest thing to do is just to leave the session on, mute your microphone, speakers, and make sure your camera's off and all that sort of stuff. But if you want to leave and then rejoin, you're welcome to do that. If you're going to exit you can leave yourself logged into Archer2 as well if you want. If you're going to exit Archer2, remember you may need to reset up the alias for srlog if you log back in, if you didn't put it in your .bashrc file in your home directory on the system. But other than that, I will see you again at 1:30, where we'll carry on with the rest of the material.